very much, and I'm very happy to closing speaker for this section. By introducing you the Neutron imaging facility at the ISIS Neutron and Neuron source. So, and hopefully you will find it useful and interesting to use for your structural integrity research. So, just a brief introduction about the ISIS Neutron and Neuron source. We are the UK's national neutron facility, and we located at the south part of Oxfordshire. It's about 20 minutes to Oxford City and about 1 hour to London. And this is how our facility looks like. We got a proton accelerator, which to accelerate the proton beam up to 84% of the light speed, and then we use this high-speed proton beam to bombard two tungsten tides, and that process generates neutrons. And then we use those generated neutrons as the particles for material research with different kinds of neutron techniques. Okay. So we are a large-scale laboratory for research. And if you have been to the Chinese Foundation source, we are a similar facility, but we are just a bit older. We have been running for over 41 years. So every year we run about 800 experiments and host more than 3,000 visits by scientists from around the world. So we very welcome the researchers from UK and from the rest of the world come to us to use our facility for research. And today I would like to introduce you one of the instruments, which is for neutron imaging, and we call it IMAT. So this is how the beamline looks like for the neutron imaging. And so the neutron imaging can be used for similar as the X-ray imaging. We can use for radiography, tomography, and also because we are a spiralation neutron source, we have the neutron beam consists of a range of wavelengths, so we can use it to do strain scanning and texture analysis based on this time of flight characteristic. And you can see the group of the beamline here is a lot of people, and you can have an idea about how big this instrument is. And imaging techniques is similar to X-ray, so we got the neutron beam pass through the sample, and we got the detector behind the sample to receive this transmitted signal. And also we can get a rotated stage, so we can do tomography, also with a Abyssal or Dragonfly. And I think why we use neutron, because there is a quite unique capability compared to X-ray. I have to say that neutron, the drawback is that the resolution is not as good as X-ray, but it has its unique capability compared to X-ray because of the interaction between the neutron, how it interact with the material compared to the X-ray, how it interact with the material. So for X-ray, it interact with the electron clouds of an atom. So when the atomic number of the element increase, also the interaction become stronger. So that makes the X-ray easier to pass through light elements, but difficult to pass through heavier elements like metals. But for neutron is a non-electric charged particle. So it actually, and it's much heavier than the electrons. So it interacts with the nuclei inside an atom. So which makes it more possible to pass through the atoms. And also it has a quite unique interaction with elements. So actually it can interact very strongly with some light element like hydrogen and lithium, while it can easily pass through with some heavy elements like metals and ions. So you can see these two images. One is from the X-ray, and the other is from the neutron. You can see the bones, but you cannot see the flesh. While the bottom one, you can see a rose that is behind a lead can, which means the neutron can pass through the lead can, and then it can be absorbed by this rose. So they have a quite unique application. And following are some examples about how neutron imaging can be used for the industry. So this one is a nozzle, fuel nozzle from an aerospace company, and they would like to see if there are any corking inside the nozzle. Hawking is a hydrogen and carbon-rich field, a residue inside the. Sorry, there is a power. Thank you. So, and also the nozzle itself is a nickel superalloy, so it's quite heavy for X-ray to penetrate. So they come to us to use the Neutron to do a radiography and tomography that allows them to find the residue inside the nozzle. And also this example is in the UKAEA, which is the UK Atomic Authority. They come to us they would like to find if there are any defects inside a critical component, which is called the diverter, which is a critical component used in the fusion reactor. And it is a copper inside and armored by tungsten outside. So because the tungsten is very difficult for X-ray to penetrate, again, so they use neutron to try to see if there are any defects inside the diverter. It's stopped. Okay, yeah. And this example is about the battery, lithium battery. As I said, neutron can have strong interaction with lithium, so it can be used to study how the lithium activity during the charging, discharging of a battery. And apart from this traditional, conventional imaging techniques, there's an advanced imaging technique called red edge imaging, which can be used to map the strain inside the component. If you have been to the diffraction diffractometer, you will know that usually there are two detectors sit at the sides of the sample, and they receive the signal from this sampling volume, and if the neutron beam satisfy the Bragg's law, you will get a diffraction peak from the detector. And if you put a 2D detector behind the sample and receive this transmitted signal, you will also get a spectrum that is a result of the Bragg's diffraction. But this time, we do not have this diffraction peak. Instead, we have an edge. That's why we call it Bragg edge imaging. And here are some more detailed explanation is that when the neutron pass through a sample, the neutron can be, the neutron interact with the material. They can be absorbed, they can be scattered, they can also be diffracted by the diffraction of the Bragg's law. And these terms are dependent on the elements itself, while the Bragg's diffraction is rely on the microstructure. So when the neutron beams, the wavelength of neutron beam increase up to a cutoff value, the diffraction, this term will disappear, and then it makes the intensity of the detector received will jump, and that generate this Bragg's edge. So from the position of this edge, because the position of the edge is related to the microstructure, or more specifically, is related to the lattice spacing of the crystal planes. So we can, from this information, we can learn the microstructure of the material. And you can see this is a diffraction pattern, and above is the Bragg edge pattern. So you can see the edge position is exactly at the same location of this diffraction peak. So again, from the shift of this Bragg edge, we can calculate the strain, similar like the diffraction. And following out some application of this technique. So this is an aluminum sample that its surface is laser shock pinned to introduce this compressive strain. So this is how the experiment set up. We have the neutron beam pass through, and this is the upper surface is the laser shock pinned. We've got the detector behind, and then we can map the strain in this direction. So you can see at the top surface, the blue area, which represents the compressive strain. And this is an industrial application, which is a turbine blade, the root of the turbine blade, which is also have the laser shock pin. So they use this technique to, again to measure the surface compressive strain. And this one is the laser welded Euro 97 sample, and they would like to map the strain of the weld because knowing the magnitude and the distribution of the residual stress is quite important for the structural integrity for this material, which is used in the fusion reactor again. And they also would like to see to what extent the post-weld heat treatment can reduce the residual stress. So they use the black edge imaging technique again. On two samples, one is as welded and the other is post-weld heat treated, and they map and get this residual strain profile. And another example is about these three U-shaped samples. Two of them, they are EDM manufactured into this U-shaped sample, and one, the first sample, is measured with black edge imaging without applying any load, which is stress-free. And the second one is measured under elastic load. And the third one is originally a straight bar, but then it is U-bent to a U shape. So that introduces a lot of plastic deformation. So you can see from the black edge imaging, the color represents the lattice parameter of the material. So for the one without stress, you don't see much variation across the sample because I have no stress applied. And for the second one, you can see a linear variation from the outer bands to the inner band because of the elastic stress applied. And for the third one, you can see the blue area in the outer half band and the red in the inner half band. And also you can see a very clear line separating these two areas, which represents the neural axis of the banding. And apart from strain mapping, this technique can also be used for microstructure analysis. And this case study is from Professor Hongbell's group, Professor Dong's group a few years ago. It's a research on the single crystal nickel alloys. The industry would like to use a single crystal for the turbine blade because of the very advanced performance. And they manufacture this single crystal using the directional solidification. And ideally, they would like to have a very well aligned single crystal, but it's never perfect. So the single crystal itself can have a slightly misorientation with a 001 grade growth. And this degree, if the misorientation is larger than 9 degrees, it can be very detrimental to the prep performance. And so knowing how much the misorientation is very important. And in this study, the researchers, they use this black edge imaging again to measure this single crystal material. But this time we don't have this black edge feature. Instead, we have this what we call black dip. And the position of the dip here is related to the orientation of the single crystal. So from the shift of this black dip position, we can calculate the orientation of the single crystal. And this black dip, we receive this black dip at each pixel of the detector. So again, we can get a 2D mapping of this gray orientation, and then we can figure out the misorientation of the single crystal. And this case study, the result they measured is the maximum misorientation is about 7 degrees to 8 degrees, which is less than the 9 degree. And after that experiment, they would like to move on to a real turbine blade, single crystal turbine blade. So in this case study, they have this single crystal turbine blade from Rolls-Royce, and then they slice it into many pieces. in the transverse direction. And then they put each of these slides into this spread edge imaging, and then they can map many of these slides of this grain misorientation, and further what they call is the boxicity of this microstructure. And then after, based on this this result, they can they can find the quantitative relationship between the dendrite growth and the boxicity, which is very important for the industry to improve their manufacturing process for this single crystal nickel-based spherules. So yeah, those are the case studies. So so now the imaging beamline can not only do the imaging, but we're also trying to do neutron diffraction as well, so that we can do both neutron imaging as well as neutron diffraction to measure residual stress. So we have put these two big diffraction detectors in this instrument. So and we will do the commissioning soon next year, and after that we can do both imaging and diffraction together. And the advantage of this beamline is that we have a large space and we have a high flux, so which means we can measure samples in real engineering size. And finally, I would like to introduce you how you can use our facility, how you can access our neutron facility. So usually we have this academic assessment for researchers from all over the world. If you have an interest to use our facility, you can put in a proposal, and then we will review all your proposal, and then we'll give you the beam time, and you can use the facility for free. And if you're from industry, you can also use our facility, and we have a flexible routes for industry. You can use it for free again as well, if you are happy to publish your data. Or if you want to keep it confidential, you can pay to us to buy the beam time, and we're also very happy to support you. Yeah. So look, the bottom is my contact, and I'm very happy to get in touch with you if you have any interest in using our neutron imaging or any other neutron techniques. Yeah, by the way, at the end of it, we've got a lot of different neutron techniques: neutron imaging, neutron diffraction, small angle scattering, and many others. Yeah. Thank you very much.